Beta?
Okay.
You may be muted.
I'm sorry, Ramiz. Actually, I am just talking locally here. Since the video is on, it appears to like that. Thank you. Okay, I request all the participants to remain muted. All the questions will be taken care at the end of the lecture.
Hello, Takaaki. How are you?
Thank you.
Good to see you. So we just start in another 3 minutes. They're live streaming on YouTube also, so that more people could join. So the session ended on time, which was nice, the previous session. So we could start this one on time as well. Hello, Shivaji.
Hello, CI testing.
Hi.
Hello, CL.
One request to all the participants, please name yourself properly because I see a lot of mobile name, speaker, some random names. Please name it appropriately. Thank you.
Yeah. Hello, Dr. Srinivasan. How are you? Are you in Ooty?
You are muted. Please unmute it, sir.
Speak. So, Gupta, Mr. Gupta, are you in Ooty now?
No, I'm in Mumbai. I was asking you, are you in Ooty?
No, we have been in Bangalore for a little while because
Okay.
Shraddha had her surgery for their hip surgery. So, and she's in the process of
Right.
recovering at the moment. She's in the home. So we're here.
Right. Okay. Well, I think in a minute we'll start. So, a good evening to everyone. I would like to extend a very warm welcome to the public lecture about to be delivered by Professor Takaaki Kajita, which is being organized by the Tata Institute of Fundamental Research, TIFR, and the Cosmic Ray Laboratory at Ooty. It is part of the symposium which is taking place, the International Symposium on Very High Energy Cosmic Ray Interactions, of which he is an organizing member as well. Since there are a lot of new people, let me introduce myself first. My name is Sunil Gupta, and I have the privilege of introducing today's speaker. Of course, Professor Kajita does not really need any introduction, but I would do so anyway, just for the sake of completeness. Long back, almost 4 decades back, Professor Kajita was studying the intensity of atmospheric neutrinos. Now, you will hear all these terms as we go along. So there are 3 names which will come again and again. One is cosmic rays, which are high energy particles coming from outer space. And when they interact in the atmosphere, they produce a particle called muon. And the muons decay to give electrons, which you all know, and neutrinos. And that is what Professor Kajita would be mostly talking about. So his work related to measurement of intensity of atmospheric neutrinos, where he wanted to really see if it agrees with our present understanding of physics. He discovered that the ratio of atmospheric muon neutrinos, there are 2 types, the muon neutrinos and electron neutrinos. The ratio in the experiment that he was conducting, its name was Cameo experiment in Japan, could not be explained on the basis of known laws of physics. Now, it is anomalies such as this that have historically proven to be fertile ground for new scientific discoveries. However, the history also shows that great discoveries are made when new and more sensitive instruments are developed by teams of experimental scientists and engineers. And that is precisely what was done by Professor Kajita and his team by developing, among other things, large photomultiplier tubes for the first time, massive water detectors, and by employing a technique called Cherenkov rim imaging. And with the help of those technologies and capabilities, he could detect electrons that are produced from decaying muons in his detector. This development led to the first important experimental indication of neutrino oscillations from the atmospheric sources in the Cameo detector. Now, oscillation is again a very fascinating term. He will describe it in detail. I'm not going to talk about it. He subsequently led his team in building Super Cameo detector, which for brevity is now known as Super K detector. And with that detector, they announced the evidence of oscillations of atmospheric neutrinos in 1998. Just how big is Super K? Well, it is big enough to fill 20 Olympic-sized swimming pools right up to the brim. That's how much water is there, 50,000 tons of it. By studying the direction of atmospheric neutrinos, he established that there were missing neutrinos, and that could only be explained through neutrino oscillations. Now, neutrino oscillations were an unexpected and possibly one of the greatest discoveries of past half century, as evidenced by the award of Nobel Prize to Professor Kajita in 2015. This discovery had a huge impact on our understanding of cosmic rays, particle physics, and cosmology, and opened doors to many other scientific fields. Professor Kajita, of course, as you would expect, is a recipient of large number of honors and awards by various scientific bodies across the world. Since I do not have much time, I would list only a handful of them. He won the 2016 Breakthrough Prize. He also has myriad other responsibilities, such as he was the co-chairman of the multidisciplinary International Neutrino Panel that was created by International Union of Pure and Applied Physics, IUPAP. And this panel prepared a detailed report for the design of the next generation of neutrino experiments. He's the chairman of IUPAP Commission C4 on astroparticle physics, and he's also the president of Science Council of Japan, which actually encompasses all disciplines of science, not just physics. Professor Kajita, to our great happiness, is also an honorary fellow of TIFR since last year. Before I call upon Professor Kajita to deliver his lecture, I'm happy to announce that he would be happy to answer your questions at the end of his lecture on the fascinating topic of atmospheric neutrino oscillations. But before asking questions, please raise your hand on the Zoom box, and then we'll come to you one by one. Takaaki, please.
Well, okay, thank you very much for the very kind introduction. Now, let me share my slide.
Yeah, please go ahead.
Oh, okay. Today, I want to talk about atmospheric neutrino oscillations. Well, Sunil already told us the detector Super Cameo Kande. And here I show the photo of the Super Cameo Kande detector. And we have been studying neutrinos with this detector. So I'm going to talk about neutrino studies with Super Cameo Kande. Okay, so this is the outline of this talk. First, I have an introduction on neutrinos and some other things. Then I'd like to move on to the early days. That means early days of neutrino studies before the discovery of neutrino oscillations. Then I want to move on to the discovery of neutrino oscillations. Then before finishing, I want to mention why we think that neutrino mass is important, and I'll summarize this talk. Okay, introduction. Well, okay, so let me explain what are neutrinos. Well, neutrinos are very small particles like electrons and quarks. And well, of course, you'd like to know more about neutrinos. And I would say that neutrinos are something like electrons, but without electric charge. In fact, this has a very significant consequence. Neutrinos can easily pass through even the Earth, as shown in this slide. But they can interact with matter very rarely. Therefore, we are able to study these neutrinos. And neutrinos have, like the other particles, three types or three flavors, namely electron neutrinos, muon neutrinos, and tau neutrinos. And neutrinos have been assumed to have no mass. Now, you may ask, how can we study these neutrinos? Of course, neutrinos are invisible. Then what shall we do? As I said, neutrinos very rarely interact with matter. For example, in this case, a neutrino could interact with a nucleus, and typically, with this interaction, a charged particle is emitted. Then we have various ways to observe this charged particle. For example, in our case, we use water. That means this particle propagates in the water. Then Cherenkov photons, or simply photons, are emitted by this particle, while this particle propagates in the water. So then, of course, we have various ways to observe these photons. So we use photodetectors to observe these photons. And this way, we observe this charged particle. And that means we observe neutrino interactions. So this way, we study neutrinos. Now, and today, I'm going to talk about atmospheric neutrinos. Now, you may wonder, what are atmospheric neutrinos? Well, from the universe, somewhere in the universe, cosmic ray particles come to the Earth. Cosmic rays are high energy particles. And once they enter into the atmosphere of the Earth, they interact with the air nucleus. Then typically, a pion or pions are produced. And pion is unstable and decays to a muon. A muon also decays to electrons. And during the decay chain of these pions and muons, neutrinos are produced. And they are called atmospheric neutrinos. So today, I'm going to talk about these neutrinos created by cosmic ray interactions. Now, I want to talk about the history towards the discovery of atmospheric neutrinos. And for this, I refer this article written by Professor Srikantan. He was the director of the Tata Institute of Fundamental Research during 1975 and 1987. And in this article, he wrote a story around 1960. Anyway, he wrote, we resumed the deep underground experiments at the coral gold fields, and the intensity measurements were extended up to a depth of 8,000 feet. By the way, this intensity measurement means measurement of the cosmic ray muon intensity at the depth of 8,000 feet, which is in fact extremely deep. At the level, in 3 months of operation, no count due to mu meson was registered. This led us to the conclusion that at such large depths, suitably designed detectors should enable us to detect the high-energy neutrinos produced in cosmic rays. So clearly, coral gold fields was the very important part of this story. Anyway, that was around 1960. And several years later, in fact, in 1965, atmospheric neutrinos were observed for the first time by detectors located very deep underground. One was located in India, Kora gold fields. Another one was carried out in South Africa. In both experiments, almost at the same time, atmospheric neutrinos were discovered for the first time. And in fact, I'd like to show one more photo of the detector at the Kora gold fields. So you see the detector in the back. And in front, several people are there. And well, I'm sorry, well, to be honest, I myself cannot identify these people, but according to the explanation, there are people, well, there were KGF collaborators from India, UK, and Japan. So this photo demonstrates that this experiment carried out in Kora gold field was the India, Japan, UK collaboration. Anyway, more than half a century ago, atmospheric neutrinos were discovered by these experiments. Now, I'd like to move on to the early days. Well, now I want to talk about the story around 1970s and 80s. In the 1970s, new theories of elementary particles predicted that protons should decay with the lifetime of about 10 to 30 years. Well, of course, 10 to 30 years is an extremely long lifetime. Well, the present age of the universe is 10 to 10 years. So compared with the age of the universe, the predicted proton lifetime was much, much, much longer. But still, people realized that it should be possible to observe the evidence for the finite lifetime of protons by suitably prepared underground detectors. So several proton decay experiments began in the early 80s. And here I list the proton decay experiments in the early 80s. From the left, this was the KGF, Kora gold field experiment in India. And again, this was an India-Japan collaboration. The next one was in Europe. The third one was in United States. The fourth one was in Japan, and the fifth one again in Europe. And well, from now on, I want to discuss the Cameo experiment located in Japan. Well, one of these proton decay experiments was Cameo. In fact, the name of Cameo came from Kamioka nucleon decay experiment. And Kamioka was the name of the town Cameo was located. In any case, Cameo was a large water detector. It had about 16 meters in diameter and 16 meters in height, and it contained 3,000 tons of very clean water in this tank. The idea was, if a proton in the 3,000-ton tank of water decay, then maybe 2 or 3 particles are emitted, and these particles propagate in the water, emitting Cherenkov photons. Therefore, we should observe these photons by photodetectors. And this way, we wanted to observe proton decays. Well, you may ask, where's Kamiokande, or where is the town of Kamioka? Well, the Kamiokande experiment was located here in the mountain area. In fact, the photo of the nearby site looked like this. And in fact, this photo was taken around 1983, I guess. So in this area, Kamiokande was located. In fact, Kamiokande was located in one of the mountains shown here. Well, in fact, Kamiokande was constructed in an active mine. So I want to show this photo. This photo was taken in the spring of 1983 when we were constructing the Kamiokande detector. And you can see Professor Koshiba at the middle in front, and he was the leader of this experiment. And in fact, he received Nobel Prize in Physics in 2002 based on the neutrino measurement in Kamiokande. Today, I'm sorry, I don't have time to discuss his work. Anyway, well, this was outside of the mine. Then we moved to the underground site and constructed the Kamiokande detector. And the construction was like this. As I said, Kamiokande tank had 16 meters in height. Therefore, we had to install the photodetectors onto the detector wall. Well, 16 meters high. Therefore, we had to be careful. And indeed, we decided to use these plastic boards to install photomultiplier tubes or photodetectors into the Kamiokande tank. So this way, we constructed the detector. Well, in fact, the construction, well, the work on the board finished within a few months. And we started the experiment in July 1983. Well, initially, we thought we would be able to observe many proton decays. Unfortunately, we realized that the true proton lifetime is much longer than theoretically predicted. Therefore, at some time, we have to be more careful. So in order to search for proton decays, we have to separate the proton decay signals from the neutrino background. And in fact, in 1986, 3 years after the start of the experiment, we developed new software to improve the proton decay analysis. But of course, we developed new software, and that means we have to test this new software. So we did various tests. And as a final test, the neutrino type, that means mu-e or electron neutrino or muon neutrino, was studied for photon-seq neutrino events observed in Kamiokande. Then we found that the number of muon neutrino events was much fewer than expected. But of course, this was a test of the new software. We thought our software is not functioning properly as we hoped. So there must be some problem in the new software. And we thought that it's very likely that there are some mistakes somewhere in the analysis. So we started various studies to find out mistakes. By the way, in the right of this page, I show a typical muon-neutrino interaction observed in Cameo-Kande. In Cameo-Kande, a typical muon-neutrino interaction looked like this. The software told us this type of event was missing. Anyway, we worked for about a year to find out the mistake. Well, even we worked hard for a year, we were unable to find out any serious mistakes. So we concluded that the muon-neutrino deficit cannot be due to any major problem in the data analysis. So at that point, we decided to publish our data. We thought it's our duty to report this strange data to the public. So we wrote a paper, and in fact, the paper was quite simple. We counted the number of muon-neutrino events so far observed in Cameo-Kande. That was about 85, and compared with the expectation, that was more than 140. So clearly, the data showed a large deficit. And also, we counted the number of electron-neutrino events. And for electron-neutrino events, the data and the expectation agreed reasonably well. So that's all we reported. Well, at that time, we simply reported this data, and we had no clear idea what was the cause of the deficit. But I was most excited with the data. And I enjoyed to find out the cause of the deficit. And in fact, before I encountered with this problem, I was working on a search for proton decays, but I changed my research from proton decay searches to neutrino studies. Well, for a while, there was no supporting data from the other experiments. But finally, several years later, the IMB experiment from the United States, which was another large water Cherenkov detector, also reported the deficit of muon-neutrino events. By the way, here I show the photo of the IMB detector. This was another large water detector. Anyway, I clearly recall the moment I read the paper from this experiment, and I was really excited to see the result. Anyway, even from the data from other experiments, we were still unable to find out the cause of the deficit. Well, to be honest, we were unable to find out the cause of the deficit. However, from the beginning, we have been thinking that maybe the deficit was due to neutrino oscillations. Well, neutrino oscillations were predicted more than half a century ago by Maki, Nakagawa, Sakata, and also independently by Pontecorvo. Anyway, according to them, if neutrinos have mass, neutrinos change their type from one type to the other. For example, in this slide, let's assume that a mu neutrino is created in the left and begin to propagate to the right. Then at some point, this mu neutrino changes to a tau neutrino. But if this particle still propagate to the right, then the type of the neutrino come back to mu neutrino, then tau neutrino, and so on. So this is neutrino oscillations. And if this is happening, we can easily explain the deficit of atomic mu neutrinos. However, well, this was at that point still just one of the ideas. So we wanted to separate the neutrino oscillation possibility and other possibilities. And for this, we thought this way. I said, neutrinos are created by cosmic ray interactions in the atmosphere. Therefore, some of these neutrinos are created above the detector. Well, typically 10 to 20 kilometers above the detector. So these neutrinos come to the detector after traveling 10 to 20 kilometers. Well, maybe 10 to 20 kilometers is just a short distance. Therefore, these neutrinos may have no time to oscillate. However, these neutrinos are also created in the other side of the Earth. And these neutrinos have to travel long distances before interacting in the detector. So typically, these neutrinos have to travel, say, 10,000 kilometers. So 10,000 kilometers is a very long distance. Therefore, these neutrinos may oscillate. So if we think this way, we can conclude that we should observe the up versus down asymmetry of the atomic mu neutrinos. And if this asymmetry is observed, that can be the very strong evidence for neutrino oscillations. However, we realized the Cameo detector was not big enough. 3,000-ton detector was not big enough. We needed much larger detector, and that was Super Cameo. Now I want to move on to the discovery of neutrino oscillations. Well, Super Cameo is in fact a very large water detector. It has about 40 meters in diameter and 40 meters in height, and it contains 50,000 tons of extremely clean water. So it is about 20 times larger than the original Cameo detector. That means we can accumulate neutrino interactions 20 times faster. Okay. By the way, I want to mention that Super Cameo is an international project. We have about 200 collaborators from 10 countries. Anyway, in order to construct the Super Cameo detector, we physicists worked in underground. So this photo was taken in the spring of '95. So this means every day in 1995, these many people worked in underground to construct the Super Cameo detector. And in fact, I think about 70% of these people were Super Cameo collaborators. So we physicists worked in underground for almost 1 year. Well, I think the construction work went well. In fact, in January '96, we started filling pure water into the super Kamiokande tank. And this photo was taken in January 96 from the top of the super Kamiokande tank. And you can see water was already filled to almost halfway. Anyway, the experiment started from April 96. And since then, we have been observing these neutrino interactions. This is a typical atmospheric mu-neutrino interaction. Here, you see many circles or dots with various colors. And the size of the circle or dots represent the pulse height, photon intensity, and the color indicates the photon arrival time. So these are the signals. And super Kamiokande observes about 10 neutrino events in a day. And we study these events as a collaboration. Well, in fact, we worked quite hard. And in 2 years, we were able to report our first important result at the neutrino conference in '98. And here, I show one of the slides we presented at this conference. And well, in fact, in the next page, I'd like to explain a little bit more on this slide. Anyway, at the end of this presentation, we concluded that the data gave evidence for mu-neutrino oscillations. By the way, this was a photo of the conference, during the conference. And you notice the presentation was quite different. Today, I'm presenting online Zoom meeting with the PowerPoint. However, in '98, we didn't have PowerPoint. So we presented the data and our conclusion based on these handwritten plastic film. Anyway, I'd like to explain a little bit about the meaning of the data. Well, here, the data showed the Gini angle distribution. And in fact, the horizontal axis shows the Gini angle, and 1 means downgoing neutrinos, -1 means upward-going neutrinos. They came from the other side of the Earth. And the black circles show the data, and the hatched histogram shows the expectation. Then you find for downgoing directions, the data and the expectation agreed quite well. However, for upward-going directions, the data showed almost a factor of 2 deficit compared with the expectation. And this data can be very naturally explained if we assume neutrino oscillations. That means mu-neutrinos created in the other side of the Earth propagate in the Earth, then while propagating, they change their type. Mu-neutrinos, tau-neutrinos, mu-neutrinos, and so on. So we concluded that this Gini angle distribution gave the very strong evidence for neutrino oscillations. And I think the world community was convinced that neutrinos indeed oscillate. Well, certainly we presented our result at the conference for physicists. However, well, something unexpected happened. On the next day, the US President Clinton, gave a talk at the MIT's commencement. And in the middle of his talk, he mentioned our result. And let me repeat what he said. Just yesterday in Japan, physicists announced a discovery that tiny neutrinos have mass. Now, that may not mean much to most Americans, but it may change our most fundamental theories, from the nature of the smallest subatomic particles to how the universe itself works, and indeed how it expands. And then, of course, as the US president, he mentioned the US contribution to Super K. Then he came back. The larger issue is that these kinds of findings have implications that are not limited to the laboratory. They affect the whole of society, not only our economy, but our very view of life, our understanding of our relations with others, and our place in time. Well, clearly, we are really honored to hear this kind of words from the US president. By the way, if you are interested in the President Clinton's talk, you can still hear at the YouTube. Well, certainly the neutrino community was really excited. And since then, various experiments have been studying neutrino oscillations. And here I show the list of the experiments that studied neutrino oscillations. The first category was the atmospheric neutrino experiments. Then people began to produce neutrinos by accelerators, then observe these neutrinos at a very long distance. These accelerator-based neutrino oscillation experiments also observed neutrino oscillations. The second category was the solar neutrino oscillation experiments. In these experiments, electron neutrinos were found to oscillate to other neutrinos. And finally, since there are three types of neutrinos, people expected that there should be third type of neutrino oscillations. And in fact, the third oscillation channel was discovered about 10 years ago. So clearly, there have been many studies of neutrino oscillations in the last 24 years or so. Now, you may ask, why physicists were so excited with the neutrino mass? Well, of course, we know that charged leptons have mass, electrons have mass, muons have mass. Excuse me. Also, quarks have mass. Therefore, you may think that it could be natural that neutrinos have mass. But still, we are excited with the neutrino mass. Why? Well, let me plot the neutrino mass in this graph. Then the neutrino mass are approximately there. So you find that neutrino mass is extremely small. And from this graph, you can read that the neutrino mass is approximately, or maybe more than, 10 billion times smaller than the corresponding mass of the other elementary particles. 10 billion times smaller, extremely small. And we believe that this is the key to better understand elementary particles and the universe. So we think neutrino oscillation experiments are very important. In fact, here I show a possible future atmospheric neutrino oscillation experiments. In fact, this is a copy of a slide I showed at the Neutrino 2018 conference. Anyway, so people are excited. We are thinking that our studies should continue. In fact, the next generation atmospheric neutrino experiments must measure neutrinos accurately. And for this, we have to accurately understand the cosmic ray flux and hadronic interactions. And therefore, we have to collaborate with the cosmic ray experiments, and one of them is the grade 3 experiment in Uti in India. Also, we think this symposium, International Symposium on Very High Energy Cosmic Ray Interactions, is very important for neutrino physics as well. Okay, now, before finishing, I want to talk about the big mystery we are facing and a possible way to understand this mystery. Well, here I show a photo of the far universe. There are many stars and galaxies. And we know that these stars are all made of matter. We know there's no antimatter star or antimatter galaxy. Well, that seems to be just trivial. However, if we think about the history of the universe that started with Big Bang, this is non-trivial. Well, in the very high energy, very high temperature Big Bang universe, always particles and antiparticles were created simultaneously. Therefore, in the Big Bang universe, the number of particles and number of antiparticles should have been equal. Then with the universe cooled down, particles and antiparticles meet and annihilate. Therefore, at present, we naively expect there should be no particle remaining. But of course, we know that there are particles, matter particles. Why? Well, in a sense, we understand what happened. In Big Bang, the number of matter particles were 1 billion 1, and the number of antimatter particles were 1 billion. They were almost equal. Then, with the universe cooled down, particles and matter particles and antimatter particles meet and annihilate. Therefore, at present, there's only one matter particle. So this way, we understand the mechanism. Well, of course, 1 billion 1 is almost equal to 1 billion, but not exactly. Therefore, we think we have to explain why there were extra 1 in the matter side in Big Bang. Well, to be honest, we do not know the answer to this question, but we think that neutrinos with very small mass might be the key to understand the big mystery of the matter in the universe. So neutrinos could be the key to understand this mystery. But let me say, this is just a, no, not just, this is in fact a theoretical idea. Therefore, we have to experimentally test if this idea is correct. So people are thinking about the next generation of neutrino experiments. And with these experiments, we'd like to observe if oscillation of neutrinos and those of antineutrinos are different. And if the difference is observed, it will be the first step to understand the origin of the matter in the universe. And well, in the last 1 or 2 minutes, I'd like to explain one of the projects that is Cameo. Well, Cameo is going to be a still larger water detector. It will be about 70 meters in height and 70 meters in diameter. And because of this extremely large mass, we expect many important research in neutrino physics and astrophysics. And we expect that the experiment will start in 2027, 5 years from now. And we'd like to work together with our international colleagues. And in fact, even at present, we have 500 members from 20 countries, including India. And the construction is going on. Okay, let me summarize. Neutrinos are really special particles. Atmospheric neutrino deficit was observed unexpectedly in protonic experiments. Subsequently, in 1998, Cameo discovered neutrino oscillations, which shows that neutrinos have mass. The discovery of non-zero neutrino mass opened the window to study physics beyond the standard model of smallest particles. Neutrinos with small mass might also be the key to understand the fundamental questions of the universe. Therefore, we'd like to continue studies of neutrinos in Cameo. And we hope we can work together with our international colleagues, of course, including our Indian colleagues in Cameo. Okay, that's all from me. Thank you.
Thank you very much, Takaaki, for a wonderful talk. And now we have a whole bunch of questions in the chat box, so I will try to read them one by one. Okay, so one of the first question is neutrino oscillation responsible for the existing of supersymmetric particle?
Oh, thank you for this question. Well, as far as I know, neutrino oscillation has no direct connection to supersymmetry.
Okay, thank you. Next question is it possible to find out tachyons by using super K or hyper K experiments?
Oh, well, okay, thank you. Well, certainly, from time to time, people checked the speed of neutrinos. And so far, we don't have any evidence for tachyons. But of course, I believe people will continue checking the speed of neutrinos.
Thank you. Okay, so the next question is, the short baseline experiment like Mini Boon, LSND, they have given a hint of 4th type of neutrino, which is of the order of 1 electron volt square. Could you please give any suggestions regarding this?
Okay, thank you very much. Well, this problem has been with us for more than 25 years. But still, we cannot conclude.
You are next.
So, in my opinion, we need to have a very sensitive next generation experiment that can give a conclusive conclusion on this problem.
Okay. Okay, but there's one more question, and then we'll go to YouTube questions. Apart from neutrino oscillations, are there any other processes that can confirm neutrino mass?
Oh, thank you. In fact, today I didn't mention anything, but well, there are experiments called neutrino-less double beta decay experiments. If neutrinos have mass, and if neutrinos are Majorana particles, then we expect neutrino-less double beta decay, namely, two beta decay happens simultaneously. However, neutrinos are not emitted. So this is really a special double beta decay. And if this is observed, that will be an extremely important discovery, in my opinion.
Okay, thank you. So I think there are some questions on YouTube.
Yes.
So
Yes.
Yari, go ahead.
Kajita-san, I'll read it one by one. First one is, what happens if cosmic rays are not come to Earth?
What happens if cosmic rays do not come to the Earth?
Yeah.
Okay, then, well, I can tell that in University of Tokyo, we will not have Institute for Cosmic Ray Research.
Okay. Okay. Another question, what are the different ways to probe the Earth's core using atmospheric neutrino oscillations?
Could you say again?
What are the different ways to probe the Earth's core using atmospheric neutrino oscillations?
I'm very...
I think my audio is something wrong.
The core of the Earth. The core of the Earth.
Okay. I will just repeat the question. I'll just repeat the question, Takaaki. This one. What are the different ways? Oh, so what are the different ways we can probe the core of the Earth using atmospheric neutrinos? Can we use them to study the Earth's core?
Oh, thank you. That is a very important question. Well, certainly, well, today I didn't discuss anything about the matter effect of neutrino oscillations. In fact, depending on the density of the matter, the oscillation changes. And by using this feature, we could study the core of the Earth. So that will be a very important topic for the future atmospheric neutrino experiments.
So the next question from YouTube is, why use only water for neutrino studies? Why not something else?
Oh, of course, you can use any other material. However, we choose water because water is cheap. Well, we didn't pay anything about water itself. Of course, in order to purify the water, we spend a lot of money, but we didn't pay anything about water itself.
Right. Also, it's transparent, right?
That's right.
Okay. So the next question is, okay, so is the other question? Do neutrinos violate CP symmetry?
Yeah, thank you very much for this question. Well, in the last 5 minutes, I discussed the future neutrino oscillation experiment. And the main purpose of these experiments is the search for CP violation in neutrino sector. And this is extremely important. This will be, if observed, this will be the first hint toward the understanding of the matter in the universe.
Right, thank you. Can we do indirect dark matter search using neutrinos? Can we search for dark matter indirectly using neutrino experiment?
Oh,
That
okay.
is the question.
Thank you. Thank you. Yes, that is a very important topic. For example, dark matters could accumulate at the center of the sun. Then these dark matter particles annihilate, producing neutrinos. And these neutrinos could be observed in large neutrino detectors. So this way, in principle, we could search for dark matter particles in neutrino detectors.
Okay. Apart from neutrino oscillations, are there other processes which can confirm that neutrinos have mass?
Oh, okay. Well, maybe 5 minutes ago, I discussed the double beta decay, neutrino-less double beta decay. That is a very important way to confirm the finite neutrino mass.
Right. Okay. So next question is, how does the discovery that neutrino have mass can help us understand that our universe is expanding? Does neutrino mass have any role in expansion of the universe?
Thank you. Well, certainly, depending on the mass of neutrinos, the expansion of the universe will change. However, what we discovered is neutrino mass is very small, and therefore the effect of the finite neutrino mass on the expansion of the universe is rather small.
Thank you. Okay. The next question is very interesting. It is asked, are there any applications of neutrinos in future?
Oh, thank you. Well, I myself have no idea. But, well, young people may have very interesting idea. And I'd like to encourage you to think about the way to use these neutrinos.
Right. Okay. So I think we'll take few more questions. There are plenty of them coming in. The detection of cosmic rays are favored at high altitudes like UT. This is from a school student. Whereas the detection and experiments of neutrinos, which are formed by cosmic ray interactions, are carried out underground. Even Cameo is 1,000 meters underground. So, is there a contradiction? Aren't they contradicting? Is this related to neutrino oscillations? So his question is why cosmic rays are studied at high altitude and neutrinos at underground?
Sunil, somehow the audio is echoing.
Oh, I'm sorry.
I'll mute it. Yeah.
Just 1 second. We'll mute the other. Okay. So the question is, the high energy cosmic rays are studied in mountains, like you mentioned in case of UT. On the other hand, neutrinos are studied deep underground. So the questioner is asking, why is it so? One thing you are studying deep underground, the other one is you are studying on mountains.
Well, thank you for this question. Well, for neutrino experiments, cosmic rays are backgrounds. Therefore, we have to carry out the neutrino experiment somewhere where cosmic ray particles do not come. And therefore, we go underground. On the other hand, cosmic ray experiments must observe cosmic rays. And if they carry out the experiment in deep underground, then there's no cosmic rays. Then they cannot study cosmic rays. So I think we are doing these experiments in proper locations.
Right. How does the discovery that neutrinos, no, this already we have asked. Okay, I think I will ask one more question and then because we are, I know you have other commitments, so okay. So can electron anti-neutrino induced inverse beta decay happen on any proton of any element, or is there any other mechanism by which one can find out what is the right material to use for basically for he's asking whether I don't know, I'm not sure whether the question is very clear. It is one girl who is asking, can electron antineutrino induced inverse beta decay can happen on any proton of any element? Okay, that is the question.
Thank you for this question. This is a very, in fact, in a sense, a very important question. That is true that inverse beta decay process, protons are converted to a neutron. However, if you are thinking about the low energy anti-electron neutrinos, then if a proton is inside the nucleus, then you need an extra energy to convert this proton into a neutron in the nucleus. Therefore, typically, you have to find out a material that contains many free protons. Then you do not need to worry about the various nuclear effects.
Right. Okay. Takaaki, thank you so much. The questions are still coming in, but I do know that you have some other commitments. So thank you very much for delivering this lecture. It has been a wonderful experience. We have large number of participants both on Zoom and YouTube. I think it's very exciting. So thank you so much, and we'll see you later in the conference.
Okay,
Thanks
thank you. Thank you very much.
Okay.
Bye
Bye,
bye.
everybody.